portion of the conical dome, we are getting the hoop reinforcement or the reinforcement due to hoop tension as 16 diameter bars at spacing 140, and at the bottom our spacing is coming out to be 190 because the hoop tension will be less here. So now this we have calculated the hoop reinforcement. Now the vertical or the slanting reinforcement along the meridian of the conical dome will be provided as minimum reinforcement on both the faces. So we calculate the minimum reinforcement and then we calculate the spacing, which is coming out to be 10 mm dia bars at 140 mm center to center. So the red lines here are showing the hoop reinforcement, which is more at the top and less at the bottom, and the blue lines are showing the slanting reinforcement, which is 10 mm at 140 center to center, which is the minimum reinforcement. So this is the design of conical dome. Now we move on to the bottom spherical dome. So the bottom spherical dome has rise of 1.7 meter, diameter of 7.2 meter. So first we find out R3 and theta 3, and we assume the thickness of spherical dome. You can take it to be 300, 150, 200 mm as per your requirement. So now what we have to do, we have to find the meridional and the hoop stresses acting in this dome. So for that you need to first calculate the load acting on this particular spherical dome. So the load acting on the spherical dome will be its self weight and weight of water on the bottom spherical dome. Okay, rest of the loads coming from the top are being taken by the bottom ring beam and the conical dome, so there is no problem here. The bottom spherical dome will be only subjected to its self weight and the weight of water coming from top. Self weight of spherical dome is 2 pi r3 h3 into thickness of dome into gamma. So this we are getting. Now here R3 is 4.67, we have calculated here. H3 is 1.7, so we get this value. Now weight of water on the bottom spherical dome is this shaded portion. The water present here and here is putting its weight on the conical dome, which we have already considered while designing the conical dome. Now the middle portion water, the volume of the middle portion water we have to calculate. So how we will do that? The weight of water in this particular area will be, if we calculate the weight of this whole cylinder and then we reduce and we deduct this much weight or this much value from that, we get the desired value. Okay, so weight or volume of this cylinder will be pi by 4 d3 square. Diameter of the cylinder is d3 into height h plus h2. So this is the overall height of this cylinder. So we are getting this formula here, pi by 4 d3 square h plus h2 as the volume of the whole cylinder, and we have to reduce this spherical this much shaded region, from this whole cylinder, because it will not contain any water. So this is basically the volume of the bottom spherical dome, the formula for which is pi by 3 h3 square 3r3 minus h3. So we reduce this volume from this volume and multiply it by gamma to get the weight of water in the acting on the bottom spherical dome, and the total vertical load on the dome will be this load plus this load, which is coming out to be 3785 kilonewton. Now we convert it into per meter square by dividing it with unit per unit area of your spherical dome. So we are getting it the per meter square weight to be 76. Now as the spherical dome, so the hoop and circumferential forces formulae will be same as we used in the top dome. So the hoop thrust on spherical dome will be W4 R3 cos square theta plus cos theta minus 1 plus 1 plus cos theta. And again I am reminding you, as we are calculating the circumferential thrust on the spherical dome, it will be maximum at 0 degree. So we substitute 0 in place of theta, not the theta 3 angle which we have already calculated here. So now hoop thrust is WR So hoop thrust we are calculating as 177, and hoop stress will be 177 divided by thickness of dome. It is coming out to be less than the permissible stresses, hence okay. And the meridional thrust we will calculate as WR into 1 plus cos theta, 1 upon 1 plus cos theta, where theta will be 50 degree 34 minutes. So we are getting the meridional thrust as this. So we calculate the meridional stress by dividing with the thickness of the spherical dome, and we check. Now, as both meridional and hoop stresses are within permissible limits, the minimum amount of reinforcement is provided on both the faces in both the directions, that is hoop and meridional direction. So we get the such types of reinforcement in the bottom spherical dome. Now we will have the design of the last component, which is the bottom circular beam. So this is the location of bottom circular beam, which is acted upon by meridional thrust from the bottom spherical dome and meridional thrust from the conical dome. So M2 we have calculated while we were doing the design of conical dome, that is 387, and M3 we have calculated in the design of bottom spherical dome, that is 217. Okay, so I have written here this value. So in bottom spherical dome, theta was 50 degree 34 minutes, and the inclination of the conical dome was coming out to be 45 degree. So the beam B3 is subjected to inward thrust from the base of conical dome and outward thrust from that of the spherical dome. So the net horizontal thrust will be T5 is equal to this value minus this value, and this value will be M2 sin theta 2, because this is the angle theta here, so this value will be the sine value. So M2 sin theta 2 minus M3 cos theta 3. Now this value is theta 3, so this angle will also be theta 3, so this component will be cos component. So M3 cos theta 3, we substitute these four values here, and we get the net horizontal thrust on the ring beam. Similarly, you can look here in this diagram also. I have made the components of the forces. This is the force M2, inclined force. This is the angle with the vertical, so this component will be M2 sin theta 2, and this is the force M3, and its inclination with the horizontal is theta 3, so this will also be theta 3, so this component will be M3 cos theta 3. So this is how we get this result. And in the vertical direction, this component is the vertical component of M2, which is coming out to be M2 cos theta 2, and this is the vertical component of M3, which is coming out to be M3 sin theta 3, because here this angle is theta 3. So this is the vertical component, and this is the net thrust. Now the hoop compression in beam is will be as this is the thrust, so the value will be, hoop compression value will be T5 into D3 by 2. Okay, as we are calculating for whole of the spherical or a whole of the beam. So 135.8, this is the hoop thrust into D3 by 2. So hoop stress will coming out to be 488 upon area. So now this hoop stress is acting on the ring beam, so this area will be the area of cross section of your ring beam. So we will have to assume this cross section here. So the hoop stress acting on the beam will be the hoop compression divided by the area of cross section, which is 0.6 into 1200, 0.6 into 1.2 meter, and it is coming out to be less than the permissible values. Now the vertical component of thrust was coming out to be 441. The role of hoop compression is just to perform this check that whether we have assumed this size of the beam correct or not. This will not be used in the calculations much. Now the vertical component of thrust was coming out to be 441, which was addition of both these components. Sorry. Apart from this, self weight of dome will also act in the vertical direction, which is 18 kN per meter cube, and we combine both these to get the total vertical load acting on beam B3 as W5 is 449. So now I will show you what is this 449. Let me open another PDF. This was the previous lecture, and this was covered in the previous lecture. So this is a circular beam, and we have now determined this W, which is coming out in our case as 459 kN per meter. So we now have a circular beam acted upon by this load, and the number of supports in our case will be 8, because if you remember in the question it was written that the tank is supported on 8 columns, therefore the number of supports will be also 8. So now if there are number of supports 8, so for number of supports 8, theta is 22.5 degree or pi by 8. So one method is you memorize all these values and we get the bending moment at support, bending moment at midspan, and maximum torsional moment as this. But if you cannot memorize it, the other method is now look at this value, this expression, bending moment at any section m phi is wr square theta sin phi minus 1 plus cos theta cos phi into cot theta. So here in our question now we have got W, we have got R is the radius of our beam, which is the diameter divided by 2, that is 7.2 divided by 2. Theta here we have 22.5 degrees, because right now I showed you the table. For number of supports 8, theta is 22.5 degree. Now we will find out the bending moment at support and bending moment at midspan. So for bending moment at support, phi will be 0 degree, and for bending moment at bending moment at midspan, the phi will be equal to theta, that is 22.5 degree. So when we substitute these two values, we will get the same results which I have written here, 0.0518 WR square and 0.0235 into WR square. So we calculate the maximum support bending moment like this, and we substitute the value of W and R, and the maximum bending moment at center as this 140. So at support, maximum support bending moment will be negative, and the positive bending moment at support will be positive, that is it will lead to hogging. So it will be this reinforcement due to this will be provided at the bottom face, and reinforcement due to this will be provided at the top face of your circular beam. Okay, now torsional moment I will explain you in the coming slide. Let us ignore or forget this formula for now. The maximum shear force we will also we have calculated as the formula for this is 0.5 WR into 2 theta. Okay, so 0.5 into WR into R into 2 into pi by 8 is coming out to be 649. This is the maximum shear force coming at support. Now from all these moments we find out which is the maximum. So 308 is maximum. So on the basis of this we select the required depth of beam by this formula under root m upon RB, where R is the design constant of working stress method, which we have calculated in the first step of this question. Now so 537 mm is the required depth. Now if you remember here in this step somewhere we assume the size of the beam 0.6 meter by 1.2 meter. So what is this 1.2? 1.2 is the depth of your beam. Okay, so we have already assumed here the depth of beam. So now we here checking whether this depth required is fulfilling that condition or not. So we have assumed D as 1200 mm, let effective cover be 60 mm, so the effective depth we are getting as 1140, which is greater than the required depth, hence we can go with this assumption. Now we do what we have done in the previous members also. Design for negative bending moment at support. The negative bending moment at support was coming out to be 308, and the torsional moment is 0, so the reinforcement required is calculated by formula m upon sigma stjd, and we get AST as this value. So using 25 mm dia bars, we calculate the number of bars. Again, I am stressing here that we are designing a beam, so we have to calculate the number of bars. So you must have always clarity in your mind which component are you designing. So this is a beam, so we are calculating number of bars, which are coming out to be 5. So provide 5 number 25 mm dia bars at support at top. Why at top? Because this is negative bending moment, so it will be provided at top. Similarly, positive bending moment design is done, and we are getting 4 number bars, which are provided at the center or midspan of the circular beam at the bottom. So this is how the bending moment reinforcement is designed. Now we go for torsional moment. So first I will explain you how we are getting this value, which I showed you here, which is 0.039 WR square. I have explained to you in the previous lecture, the value of torsional moment is not fixed where it will be maximum. So first we have to find out the value of phi where torsional moment will be maximum, and then we will find T phi using the expression for torsional moment. So let torsional moment is maximum at a point P at an angle phi from the support. Okay, so how we will get the value of phi to get maximum torsional moment? So this is the expression. This is the expression used to calculate that. How we are getting this expression, I will not be explaining to you here. Now in this equation, sin phi, here phi will give you the value or the angle at which, or the point at which the torsional moment will be maximum. So theta, we have for our beam, theta is 22.5 degree or pi by 8, and we substitute this value, all these values here, to get phi is equal to 9 degree 31 minutes. So let me tell you one thing here, whenever you are solving such questions, make sure that if you are doing calculations in radians, then all angles should be in radians. If you are doing calculations in degrees, then all angles should be in degrees. Radians must be preferred mostly, because in such cases radians are better. So if you have pi by 8, then you calculate pi by 8 and you write its value here and then get the value of phi. So by using calculator I have solved this, and phi is coming out to be 9 degree 31 minutes, which we can change from the calculator to 0.166 radians. So what does this mean? That at an angle of 0.166 radians or 9 degree 31 minutes from support, the the torsional moment will be maximum. Now we calculate the value of torsional moment at this point P, which is at 0.66 radians. So this is the expression for torsional moment. So WR square phi minus theta plus theta cos phi minus theta sin phi cot theta. So phi we get as 0.166, theta is pi by 8. So I am doing all the calculations in radian. Although I have written here 9 degree 31 minutes, but when I solved this question I changed it to radians and then I did the calculations. So here it will be 0.166. Okay, so you can write here 0.166 also, there is no problem. So from when I solved it, I got this expression, that is 0.0039 WR square, which is same as this. So this is how we get this expression. So one method is you remember all these, you can directly remember this expression for for different values of theta or different values of number of support, and the actual way is this. Now we are getting this value for 23.2 kilonewton meter. So torsional moment at phi is equal to 9 degree 30 minutes from support is coming out to be this. Now we will now design the torsional reinforcement in the same way as you must have studied in the design of RCC structures part 1 when we studied the limit state of torsion, where we designed the torsional reinforcement. Whenever we are considering torsional moments, we have to find the equivalent bending moment, which is the combination of torsional moment and bending moment at that point. So previously in this question we have calculated the bending moment at support and bending moment at center, but we are concerned with the point where the torsional moment is maximum, because the torsional reinforcement will be provided where the torsional moment is maximum. So we have to find out the bending moment also where the torsional moment is maximum, which is at phi is equal to 9 degree 31 minutes. So m at 9 degree 31 minutes is formula for the general expression for m phi is w r square theta sin phi plus theta cot theta cos phi minus 1. So we substitute here theta is equal to 22.5 degree or pi by 8 is equal to 0.3926 radian. So I have converted pi by 8 2.5 degree into radian, which is 0.3926 radian, and phi is equal to 9 degree 30 minutes also into radian, which is coming out to be 0.166. So we substitute these values here to get m phi is 0.44, and this is the bending moment at this point P where torsional moment is maximum. So now we have got the value of torsional moment at phi is equal to 9 degree 30 minutes and bending moment at phi is equal to 30 minutes. Okay, 9 degree 30 minutes. So now I will show you how we design the torsional reinforcement. For this I will open another PDF. So this you must have studied in your previous courses of RCC1. Then longitudinal reinforcement is provided in as torsional reinforcement to resist equivalent bending moment of mu plus mt, where mt is tu 1 plus d by b upon 1.7. Here m is the bending moment at that particular point, and t is the torsional moment at that particular point. So this similarly we are doing it here also. The m equivalent is m, that is the torsional bending moment at that point, plus mt, where mt is the torsional moment at that point into 1 plus d by b upon 1.7, where d is the total depth of your beam, b is the width of your beam. T we have got here 23.2 and m we have got as 0.44. So we substitute m is equal to 0.44 and mt we calculated as 40.94. So equivalent bending moment is 41.38. So we provide the longitudinal reinforcement in the circular beam due to this particular moment, which is the equivalent bending moment, and this is calculated by m upon sigma stjd. It is coming out to be 374. So assuming diameter of bar 20 mm, we get 2 bars. So 2 bars of 20 mm diameter at top and bottom at phi is equal to 9 degree 30 minutes is provided to resist the maximum torsional moment at 9 degree 30 minutes. Now I have written here 0.6 meter also, because 0.6 meter from support, because when you are at site you cannot tell that provide this much reinforcement at phi is equal to this. Okay, it will be very difficult or impossible to do such calculations at site. So we have to when you are giving your drawings or giving the design to someone, you have to give the exact location of that point. So if this was your beam, okay, and we have found the maximum torsional moment at this point, which is phi, which was at P, which was at an angle of phi. So this is your support and we are talking about this point. So we have to basically find out this particular distance. So as this is an arc, you know from trigonometry that phi is equal to length of arc upon the radius, so L upon R. So R here is 3.6 meter for this particular beam, phi is 0.6166 radian, so L, that is the length of arc or the distance of this point from the support we will get as 0.6 meter. So therefore, to summarize the reinforcement, we have calculated 3 reinforcements. First reinforcement at the support, negative bending moment, that is provided at top. We have got 5 number 24 mm diameter bars, and at bottom we have found 4 number 20 mm diameter at the center. And apart from this, we have also found out 2 bars of 20 mm diameter at top as well as bottom at this particular point. Okay, so we combine all these to get the reinforcement at top to be 5 number 25 mm dia bars near supports. And as you know, at top, if I go back, this reinforcement is provided at top near the support only. Okay, so actually we required 5 bars at the support portion of top face, but for safety we can extend some of the reinforcement in the middle portion also. For example, if this is your beam, then and in the support region, if this is the length of the beam, in the support region we have to provide 5 bars. Okay, 5 bars. And in the middle portion at the top face, there is no requirement of reinforcement because there are no bending moments, but for safety we can extend any 2 bars and curtail 3 bars and extend 2 bars. So I have written here in this bracket that out of the 5 bars we can curtail 3 bars up to this near the support and extend the 2 bars towards the center for better safety. Now at the bottom we have 4 20 mm dia bars at the mid span. Okay, so similarly, if this is your beam, in the bottom portion we require 4 bars near the mid span only. 1 2 3 4. If this is the middle portion of your beam, so we require 4 bars at the bottom face in the mid region. But as we have already also got 2 bars of 20 mm diameter for the torsional reinforcement, and for safety purpose we cannot keep the bottom portion totally empty, so we can extend all these bars from here to here for better safety. Okay, so that's why I have written here 4 20 mm dia bars throughout. So this is how this line has been written. You can designer can do according to him or her that whatever is suitable, but we must take into consideration all the reinforcement at top, reinforcement at bottom, at support, at moment, and the torsional reinforcement also. So this is the design for the main torsional reinforcement. Now we will design the shear reinforcement for torsion. Now at support we had got shear force to be 650 kN. If I go back here, shear force is 650 kN. Now shear force at the point of maximum torsional moment, we are only concerned with the point where there is a torsional moment maximum, which is this point. So Vt, that is shear force at the point of maximum torsional moment, will be Wr into theta minus phi. So we are getting it to be 374.43. Now again I will go to the other PDF, and here you can see that the equivalent shear force in torsional reinforcement is calculated in this way. V is equal to V plus 1.6T upon B, where V is the shear force acting at that point and T is the torsional moment acting at that point. So V is 374.43, 1 plus 1.6 into 23.2 is the torsional moment, maximum torsional moment, and 0.6 is the width of the beam. So this is the equivalent shear force. Similarly, the equivalent shear stress will be V equivalent upon BD. So this will be 436 into upon 600 into 1140. So this is the tau V for our this particular shear force. Now as we do in case of design of shear force, we first calculate tau V, then we compare it with tau C max. It should be always less than tau C max, and when this check satisfied, then we compare it with tau C. So here tau C max for M30 is 2.2. You can check your IS 456, and then we calculate tau C. So this check is okay. Now we calculate tau c. So tau c depends on the percentage of reinforcement, main reinforcement, and the grade of concrete. So first we find out the percentage of reinforcement at this particular point. Phi is equal to 9 degree 30 minutes. So you know here from this point that at the bottom portion, which is the tension phase, all the reinforcement is 4 number bars of 20 mm diameter. So you can calculate the percentage of reinforcement as this 100 into 4 pi by 420 square upon 600 into 1140. So for PT is equal to 0.18% and grade of concrete as M30, you can find out the tau c from your tables of IS 456, and now we can compare tau c with tau v. So as tau v is greater than tau c, therefore shear reinforcement is required. So the area of shear reinforcement is calculated in this way. The area of shear reinforcement is such that ASV should be equal to T upon V1 D1 into X plus V upon 2.5 D1 into X, okay, where X is the spacing of the shear stirrups, and 0.87 Fy is the basically the shear strength or the strength of the material of the reinforcement. And B1 D1 are, B1 is the center to center distance between corner bars in the direction of width. So this is the B1, center to center distance between the corner bars, and D1 is the center to center distance between the corner bars in the direction of depth. So we substitute it here, T into SV upon B1 D1 sigma SV plus V upon SV. This is the same formula which I have shown you. Now we calculate B1 and D1. So as you can see here, for calculation of B1, we are doing it in direction of width. Width of the beam in our case is 600 mm, and this 40 is the cover and 25 is the diameter of bar. So 25 by 2, 25 by 2 in both directions will give you 25. So this is the B1, and similarly we are getting D1. So here ASV and SV both are unknown, so we find out this ratio, which is coming out to be 1.05. Also, as per IS code, ASV and SV should be greater than this particular value. So we find out ASV SV upon SV ratio here like this, and we find out here, and we compare both these two. So ASV upon SV ratio from this criteria is tau v minus tau c upon sigma c into v. So this is coming out where tau v is 0.64, tau c is 0.32, sigma SV is 130 and v is 600. So this we are getting as 1.47. So according to this expression, our ASV upon SV should be greater than 1.47. But here our ASV upon SV was coming out to be 1.05. So we will take this value. Okay, so I think you are able to understand how we get to this portion. So now what we will do, we will assume the diameter and the diameter of your shear stirrup, and we can calculate the spacing easily. So here I am using 4-legged 12 mm die bars. You can use 2-legged also. So the area of one stirrup will be 4 into pi by 4 into 12 square, and from this we have got ASV upon SV ratio to be 1.47. So SV we are getting 307 mm. So SV should be less than or equal to 307 mm. Also I will take you to this one another specification here. This specification is from code that the spacing of stirrup should not exceed x1 plus y1 by 4 and 300 mm, where x1 is the shorter dimension of stirrup and y1 is the longer dimension of stirrup. So now we are concerned here with x1 is the shorter dimension of stirrup and y1 is the longer dimension of stirrup. We have to deduct the necessary dimensions to get the value of x1 and y1. So one SV value we have got from here. Okay, first that SV should be less than this. Second value, spacing should be less than 495. x1, where x1 is 495 plus 25 plus 12. This is the dimension of stirrup in the shorter direction, and it should be less than x1 plus y1 by 4. It is coming out to be 421. y1 is this, okay, and it should be less than 300. So you compare all these together and you choose the spacing to be the least of all these four values. So we will get the spacing as 300 mm center to center. So we are providing 12 mm dia 4 leg stirrups at spacing 300, and as this is a very deep beam, because the depth of the beam is 1.2 meter, which is greater than 450, we have to provide some side face reinforcement also as 0.1% of the cross section. So we are providing two 16 mm diameter bars on each face of your ring beam as the side face reinforcement. So this is all about the design of circular beam. So to summarize, what we did here was, first we found out the loads acting on the circular beam, and the vertical load coming out was this much. Then we found from the number of supports we got the semi-vertical angle of the circular beam, and we found out the maximum bending moment at support, maximum positive bending moment at center, and then we calculated the required reinforcements for both these moments. Then we found out the torsional moment at maximum value of torsional moment. For that we first found out the location of the maximum torsional moment, and then we calculate the T5. Then we calculate the bending moment at the point of maximum torsional moment also, so as we can get the equivalent moment. So the longitudinal reinforcement due to the torsional moment we will get from this equivalent moment. So we provided this reinforcement and the bending moment at top and the bending moment at bottom reinforcements, and combine these together to get this reinforcement in the ring beam. Then we designed the shear reinforcement for the torsional reinforcement like in this way, and then we calculated the side face reinforcement. So now we are done with all the design of all the components. Now I will summarize all the detailings. So let's look from the top. So the top dome, the thickness of top dome was 75 mm. Okay, let me zoom it. So if we move from top, the top dome thickness we had assumed to be 75 mm, and we had made the necessary check for it too. And the diameter and the reinforcement which we got was 8 mm dia bars at 190 mm center to center in meridional and the hoop directions. So this is the meridional direction, and these dots are showing you the hoop direction. And as you can see, this meridional reinforcement is continued to the top ring beam so as to provide proper connection between the top ring beam and top dome. Then in the top ring beam we had got 8 number rings of 12 mm diameter, and apart from that it were tied together by stirrups of 308 mm diameter and 300 mm center to center. Okay, now again then we have the cylindrical walls. The main reinforcement is the hoop reinforcement, which is provided with lesser spacing at the bottom and increasing spacing towards top. So in this region we had 16 bars of 120 mm center to center hoops. Here in the above middle portion we had 16 diameter bar at 240, and in the upper portion we had 16 diameter bar at 300. And the vertical reinforcement in the wall was 10 mm dia bar at 140, and this vertical reinforcement is also continued to the top ring beam as well as to the conical dome also somewhat here. Okay, and now we have the bottom ring beam, in which we had got 25 number rings of 20 mm diameter and 10 mm diameter at spacing 150 mm center to center stirrups. Okay, and then we had the conical dome, in which we provided two types of reinforcement. One was the slanting reinforcement, which we had provided at the minimum reinforcement 10 mm bar at 140 center to center, and the hoop reinforcement due to the hoop tension forces, which were maximum here and minimum here. So here the spacing of the hoop reinforcement, these dots are showing the hoop reinforcement is 190 mm center to center, and on the top it was 140. So these reinforcements should be kept together, and here the spacing should be increased. The thickness of the top, also keep on looking at the dimensions of the bottom ring beam, the thickness of bottom conical dome. Then we have the bottom spherical dome, in which we provided meridional and hoop reinforcement in both directions as 10 mm dia bar at 200. And then we have the circular beam. Here we got 4 reinforcement at bottom and 5 reinforcement at top, where I have shown here only 2 because this section is probably at the middle portion. So here 5 reinforcement we provided near the support at top and 2 are provided near the middle of the top portion. This is the side face reinforcement, which you can see here, 216 mm diameter on both faces, on this face also and this face also. Then we had provided the shear reinforcement also in the circular beam. So I have made here cross section of circular beam at support and at midspan. Okay, so that you have better understanding. So circular beam cross section at support will have 5 number bars at top, because the negative moment are maximum at the top region near the support, and 4 at the bottom. Apart from them we have 2 side face reinforcement, and then we have 4 legged 12 mm dia stirrups at 300 mm center to center. In the midspan region we will have 2 reinforcement at top and 4 at the bottom, and 4 leg 12 at 300 center to center. You can also calculate the shear reinforcements at different points, like shear reinforcement at support, shear reinforcement at midspan, and you can change it. But I have not done so. I have taken the same reinforcement 4 legged 12 mm dia bar at 300 center to center throughout the circular beam. So this is all about the design of Intze tank. I hope you understood it well. So although this problem is very lengthy, but if you look at the individual components, the design is not so tough. You just need to find out the loads which are acting on each component first, and then we design the reinforcement and decide the dimension. So from top towards bottom we move in this way, and you have to know the structural behavior and what kind of reinforcement and what kind of load each type of component will take. So this is the complete design of Intze tank, or overhead tank with top dome and bottom conical and spherical dome.